Forget. You never saw anything. Hello, welcome back to Luke's Lessons in Organic Chemistry, lesson number 2. Let's start off by talking about dipoles. So, let me get my notes out. Dipoles are a result of an unequal distribution of bonding electrons between atoms. So, in regular covalent bonds where both atoms are the same electronegativity, call them X1, bonded to X2. They share these electrons perfectly between them in kind of like a cloud, but we'll just represent it as these two being directly in the center of these. These are equidistant. Polar covalent is when you have X1 being less electronegative than X2. You kind of get an electron cloud that more favors the more electronegative one. It's kind of an exaggeration I got going on over here, but it'll be more, the electron cloud will lean more towards the electronegative one, because it's more like the electrons are more likely to be on this side than this side. That's all the cloud is. And we can show that as something being delta negative or delta positive. The delta just means slightly. So slightly negative or positive. And we also show this by writing out dipoles. I've already started it here, but we go from the partial positive to the negative, and we write a little plus on the positive side. In ionic bonding, the electrons are just completely stolen by the larger molecule. So this would be your halogen, or yeah, like your halogens and stuff, and this would be your metals and metalloids and such like that. Ionic bonding doesn't really come up in organic chemistry, but polar covalent and covalent bonds definitely do. Way more polar covalent than covalent bonds. But covalent bonds are obviously still there. We just don't really care about them because they don't create dipoles. But polar covalent do, and ionic definitely do. Big dipoles. And so figuring out the dipoles, we have our electronegativity chart. You just kind of have to, there is a way to figure out for one thing to be more electronegative than another. Sorry, I should have added a picture of a periodic table in here. Forgive me for not doing that. So electronegativity will increase as we go along, and it will increase as we go up. So helium is going to be way more electronegative, or yeah, way more electronegative than like potassium, which is down here. And helium is going to be less electronegative than, or sorry, I keep saying helium. Hydrogen is going to be less electronegative than helium, which is over here. But oh, actually, I'm wrong. It stops at here. So, sorry, there's like a lot of atoms in here, but like hydrogen would be less electronegative than carbon, which is over here, oxygen and such. As we can see here, hydrogen is one of the lower, or the lowest ones, along with phosphorus. And then we have carbon, which is over here. Fluorine is our most electronegative because it is way up in the corner. It is right next to the noble gases, which aren't electronegative at all, because they don't have, they already have their stable octet. They have 8 valent electrons, where this fluorine has 7, and it really, really wants just one more. electron, so it's really electronegative. It really wants that electron. Oxygen is also very electronegative. Just kind of get in your head a couple of these numbers. We don't really need that one or that one, but all of these are pretty important. For our formal charge is looking at things that are definitely positive and definitely negative. No more delta this, delta that. So for an example here, I have ammonium and ammonia. So ammonia, I'm going to start out with is NH3, which will look like this. We have N here, H, H, and H, with our electron group up here. So the formal charge is equal to the number of valence electrons. If we look at our periodic table, we can see that nitrogen has 5 valence electrons. Then we'll minus the number of bonds and minus the number of electrons. So we have 1, 2, 3 bonds, and we have 1, 2 electrons. And so we will come out to a formal charge on this nitrogen, and only this nitrogen right here, that's all we're checking for, will be equal to 0. We can also check it for these hydrogens, but hydrogen only has 1 valence electron, so if it's bonded at all to anything, it'll just be 0. So if we see a hydrogen, we don't need to worry about it. And now I'm going to show you ammonium, which is NH3, or which is NH4, forgive me. And that'll look like this, just like our ammonia, but with just one more hydrogen on it. God, I'm really bad at writing with a mouse. And so our formal charge will be equal to the number of valence electrons, which we know is 5, minus the number of bonds, which is 1, 2, 3, 4, minus the number of electrons. We no longer have this electron pair up here because we bonded it to a hydrogen. So we have 0. And our formal charge for this nitrogen is going to be plus 1. So we can add a little plus 1, because if the nitrogen is plus 1 and nothing else cancels it out, which we know all of our hydrogens won't cancel it out because they're bonded to something. So we know that the entire molecule is plus 1. This is also important for later on down the line for carbocations. This is because we have 4 valence electrons minus 3 bonds minus 0 lone pairs, which equals positive 1. So this would be a nitrogen cation, and that would be a carbocation. Stabilization. So here I'm going to talk about resonance structures, which are the same, which have the same chemical formula, structure, stoichiometry, but different placement of electrons. Here for my example, I have, let's draw it out, 1, 2, 3, 4, 5, 6. Let me throw double on there, double on there, double on there. Oh. Okay. So this structure and this structure, you will notice that we didn't break any pi bonds, or we didn't break any sigma bonds. I'm not sure how to write sigma. But we did move around our pi bonds. We took this one and we chucked it onto this oxygen. Then one of these lone pairs came over onto this carbon. which is why it is negative. This lone pair moved over, and this lone pair moved over. And that's how we got this. So nothing changed about this. This is still C, oh, God damn it, C6, H, C6, H5, O, and this is still C6, H5, O. Nothing changed, nothing happened, it's all the same, but now we have different configuration of electrons. We can only move pi bonds, and compounds with resonance structures are more stable than those without because there's less of a chance for another molecule to hit the exact right GHT spot for bonding. So I'm just gonna make up a hypothetical here. We have a hydrogen that's like just floating around the place. If this is constantly switching between these two, this hydrogen, this positively charged hydrogen, will be able to attack these electrons over here and make OH. But since it's since some of it is in this form and some of it is in this form, the hydrogen can't attack this one because this one has a formal charge of 0. This oxygen right here has a formal charge of 0. And this one has a formal charge of -1. This hydrogen is going to want to react to that, but it isn't going to want to react to that. I'm sorry, these are getting a little messy, aren't they? But yeah, that's just less likely for anything to be able to come in and just hit something randomly at any time. And then electrons, as I demonstrated in this last one up here, don't just jump from like one end of the compound to another. So let's take the same one. Right, we have started off with a double bond here, double bond here, double bond here. And if it was slightly different, just know that this is also in resonance with itself, but those double bonds moved to over there. So we have O. So say I wanted to, instead of having my negative charge move to here, say I wanted it like over here or something for the purposes of like making synthesizing reactions. It would first, this structure would first have to become this one with our, wait, sorry, hold on. Yeah, right, yeah. So this double bond had to move up here. Oh, wait, sorry. That's not how that works. This moves over here, and this moves over here. So this O forms a double bond, and the double bond that was here was taken, and those electrons were put on this carbon, which makes it negative. And then we can take this one, these electrons, move them onto here to form another double bond, and take this pair of electrons and move it onto this carbon to make it negative. Now we have it where we wanted it to be in the beginning. Although we had to change the bonding in a couple places. Fuck, I'm really trying to remember where the fuck I'm supposed to put these. There we go. Perfect. That's all that needs to be done with that. And there's one other thing called anion stabilization. This just basically means that a compound is more stable when the negatively charged atom is an electronegative element. So, sorry, you wouldn't want a carbon to be negative. This happens way less often than oxygen being negative. if we can tell by going back to here, we can see that our carbon has a lower electronegativity than oxygen. And so it's less likely to be a negative element. It's less stable as a negative element. But oxygen really wants electrons. Fluorine really wants electrons. All these do. These want less of it. So they're less likely to just be floating around space as something negative. And then the last thing I want to talk about is an introduction to arrow pushing. That's kind of what I'm doing back here with, you see these arrows like showing the movement of the electrons. That's all that is arrow pushing. It is just the visual representation of the movement of electrons going from source to sink. So source, an electron source would be either a double bond or a lone pair, because we can move those around in our resonance structures without changing the general structure. So those are always kind of just free to move around the molecule wherever they want, given our rules of stabilization and unstabilization here. Like obviously they're not going to move to like a hydrogen or something. But that should be all. Thank you for watching, and have a nice day.